Suppose biker guy wants to impress his friends with a really cool jump, all right? So he starts off and he's cruising along and he wants to jump down to a lower level over a chasm, but he wants to just barely make it. If he's going too slow, he's going to fall into the chasm, and that's no good. But if he's going too fast, it's going to look too easy, right? He's just going to fly over the top and people will go, oh, well, that wasn't much of a chasm at all now, was it? So he wants to go exactly as fast as he needs to in order to make it. Now the question is, how fast is that? The good news is, you already have all the tools you need to answer that question. You have the kinematics equations. The kinematics equations are the same whether you're talking about two-dimensional motion as you are one-dimensional motion. Also three-dimensional motion, which we're never going to use in this class. So two-dimensional motion uses the same kinematics equations that we've been using all along. And you already know those. So that's one thing, is you've already got the tools in your toolbox. The second thing you need to know is that perpendicular things don't affect each other. There's a fancy physics word called orthogonal. Anything that is mutually perpendicular. So you have this way and this way, those are perpendicular, and then this is perpendicular to both of them. These are all orthogonal directions. Well, orthogonal vectors don't have an impact on each other. So what you have is an object moving sideways and an object falling. Those are two different problems that you've already done in class by now. And moving sideways uses just one equation. It's the easiest equation for motion, actually, because there's no acceleration sideways, right? If there's no acceleration, you just get velocity equals distance over time. That's it. Now, when you're moving through the air, like when he's on the ground, maybe he could accelerate or hit the brakes or whatever, but while he's in the air, it doesn't matter if he hits the gas or the brakes. He's not touching anything, so he's going to move at a constant speed sideways. V equals displacement over time. That's it. Now, vertically, on the other hand, he is falling, right? And so there is acceleration, so we can use all of our other kinematics equations. And that's the key idea behind all projectile motion, is that horizontally you only have one equation, and it's the one without acceleration in it. And then vertically, you have all of the other equations. You can use everything except the equation that doesn't have acceleration in it, because you have gravity pulling down on you all the time. So, to answer this question, let's get rid of the books and throw in some kind of real-life numbers, assuming his bike is about 2 meters long. That makes the lower ledge 6.5 meters from the ground, the higher ledge 11 meters from the ground, and the chasm 3.7 meters across. So the first thing to realize is that because we get to pick our reference frame, we can make this a little easier. Instead of using 6.5 and 11, we can just call this lower level 0 and use 4.5 meters as the height for our problem. To solve this, we're going to use the distance formula, but it's important to point out that everything is in the y direction. So even though the bike has velocity when it's leaving the cliff, that is velocity in the x direction. That is horizontal velocity. The velocity in the y direction when it leaves the cliff is 0. This is identical to asking a question, how long does it take an object dropped from 4.5 meters up to hit the ground? Knowing that, this is as easy as use the right formula, plug in, and solve. The answer is 0.958 seconds to hit the lower level. And now that you've used the y direction to get the time, say to yourself, hey self, there is only one equation in the x direction, and then use that equation, plug in the number you just got, and solve. The answer is 3.86 meters per second, or about 8.5 miles per hour. So there it is. That is the simplest type of projectile motion question. An object leaving a cliff horizontally. It could be a bike leaving a cliff. It could be a bullet fired horizontally. It could be any number of things. A baseball thrown horizontally. Anything that is thrown horizontally and then falls is the easiest and most basic type of projectile motion problem. Simply use the y direction to figure out time, and then use the x direction to figure out whichever thing you don't know, right? In the x direction, you only have v equals displacement divided by time. So v, d, and t, or vx and t if you're in AP Physics, just you're going to have two of them. Figure out the third one. Simple. And one final detail involving projectile motion. The Earth is curved, right? The Earth isn't actually flat. Now, it's not curved by much. For every 8,000 meters you go sideways, the Earth curves 5 meters down. That's really hard to draw. It's really hard to see. There's a reason why idiots believe in a flat Earth, right? Because it looks kind of flat. There's lots of things you can do to prove that the Earth's not flat. Maybe I'll make another video of that sometime. But anyway, the Earth is curved. And 5 meters, 4.905 meters precisely, is how far something falls in 1 second. So if you can go sideways 8,000 meters in the same time it takes you to fall 5 meters, then 8 kilometers sideways, 5 meters down, you're actually no closer to the Earth than when you started. And your direction has changed to still be tangent to the Earth at that new point. And so you're going to go another 8,000 meters, and then fall 5 meters, and then 8,005, and 8,005, and 8,005. And what's going to happen is you're going to fall around the Earth. That's what a satellite is. A satellite is an object that is falling around the Earth. Or the Earth happens to be falling around the Sun. The acceleration there is not 9.81 meters per second squared, but it's just right to have us going in very close to circular motion. This falling around objects is what satellites are doing. That's exactly it. So satellites are falling, and that's pretty cool. Now you might ask yourself, why are astronauts weightless on the International Space Station if there's gravity that's causing them to fall around the Earth? And that's a great question, because they are experiencing gravity. In fact, where the International Space Station is, they're about half the weight that they are on Earth. But I weigh a little over 200 pounds, and if something weighs 100 pounds, it's not floating, right? So the details of that we're going to get to much later when we talk about gravity and circular motion in more detail.